Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And in this video, we're going to continue forward with the rational roots theorem by showcasing a few examples. How do you use it? The first two videos covered kind of the motivation of the rational roots theorem and then the actual theorem itself in a proof. And now we get down to actually using it. It can be a very powerful theorem if it can be used conveniently. So here's the how-to. How to factor a polynomial with integer coefficients, remember that's a requirement, using the rational roots theorem. I'm going to go ahead and highlight that integer coefficients is critically important. First thing you're going to do is write down all factors of both the leading coefficient and the constant term. There could be quite a few there, so don't be too intimidated if there's like a lot. We have tactics to make our life a little bit easier. Write down all ratios of factors, and when I say all, really I should just say some. Write down some of the ratios of factors to the constant term to those of the leading coefficient. And then, like I said, to be honest, I don't write down all of these. I just start with the list, and when I get bored, I move on to step 3. Now, starting with the easy ratios, the integers is usually a really good idea. Use synthetic division to check if a ratio is a zero of the polynomial. Remember, when you use synthetic division, or basically by the remainder theorem, when you use synthetic or long division, the remainder tells you what the value of the function is at that zero, or at that value, sorry. And if the remainder is 0, then that means that you have a 0 at that point. And that's actually by both the remainder and the factor theorems. So again, you want to find out that your remainder is 0, because if it is 0, then you know that that value must be a 0 for your function. That's exactly what you want. And therefore, x minus that 0 will factor out. So once you find a 0, let's call it c sub 1. Now your polynomial is of this form, x minus c sub 1. And then you times a new polynomial because you've just factored that out. And you continue that process. You just continue going through and checking to see. By the way, you do want to check to see if, for example, your, let's say you found out that 2 ends up being a 0. So x minus 2 must be a factor. You should probably check for that 2 to be a 0 again, because you can have zeros of multiplicity more than 1. And that's exactly what I say here. You should recheck that one more time because it might be of 0 of multiplicity more than 1. And you just continue that process until you get down to a polynomial that is either quadratic or that can be factored pretty easily. And I don't know why this did a capital I there. I'll fix that in my lecture notes. So let's just jump right into it. Find all rational zeros of the polynomial function and then factor. So let's go ahead and just take a look at all of the ratios of the lead coefficient, the ratios of the constant term to the lead coefficient. And I actually do this by writing the constant term and the leading coefficient. And then I go through and say, okay, well, the factors of 9, let me zoom in on that, are plus or minus 1, plus or minus 3, and obviously plus or minus 9. Those numbers divide nicely into 9. And plus or minus 1 divides into 2, and plus or minus 2 divides into 2. I write it this way because this is going to be the numerator, and that will form the denominator of my candidate zeros. So I'll write that off to the side here, my candidate zeros, because you might, it might be useful to see kind of how they all look. So notice it's just going to be the same list right here, 1 plus or minus 1 over plus or minus 1, and then plus or minus 3 over plus or minus 1, and then plus or minus 9 over plus or minus 1. So you're always going to have that first, your top list will always be the first set of candidates. And then you have to include all those same numbers, 1, 3, and 9, divided by the 2. So I'll actually write it down below. Plus or minus, let's see, we have 1/2, plus or minus 3/2, and plus or minus 9/2. Now, do I want to try all those combinations? I don't know if I want to try all of them. I think I'm going to do this. And I don't know, by the way, how this factors. So I'm just going to start with those 3. Notice I didn't jump to the 9. There's a very specific reason I don't go to large numbers very early on. And that's mainly because synthetic division causes the numbers kind of explode a little bit. So I'm going to take that polynomial and I'm going to see if positive 1 is a 0. To check if positive 1 is a 0, I'll use synthetic division. Remember, you take the coefficients, the 2, the 1, the negative 19, the negative 9, and the positive 9. You get really good with synthetic division in this course just because you use it quite a bit. Bring down the 2. 1 times 2 is 2. Add those up. 1 times 3 is 3. Add those up. 1 times a negative 16 is a negative 16. There's really no need for me to add these up because I can already see that the next step won't lead to 0. 1 times the negative 25 is negative 25, and this is not going to be 0 when I add them up. So that tells me 1 is not a 0. It's a very quick check. Now I'll move on to the negative 1. So here's what I'll do here. I'll go ahead and maybe erase the positive off that. Now I'm going to check the negative 1. So I repeat that same process. I'll do this over here, negative 1. Again, you have a 2, a 1, a negative 19. Let's see, a negative 9, and a 9. You bring down the 2. 2 times a negative 1 is a negative 2. Add them up. Negative 1 times negative 1 is 1. Add them up. Negative 1 times negative 18 is 18. Add those up. Negative 1 times 9 is a negative 9, and we get a winner. When you have that remainder of 0, that means that negative 1 here was actually a 0. So I happen to know. Now, this is not what I recommend doing, but I'm going to showcase what this means. This means that x minus that negative 1 is a factor. And what you're left with is 2. I'm just stealing all my coefficients from here. Okay. I'm left with 2 times x to the third, reducing the power of this by 1. So 2 times x to the third minus 1x squared minus 18x, and then plus 9. Now, technically, I could factor that using factoring by grouping, but let's suppose that you didn't see that, okay? So what do you do now? Let's say there was a big old polynomial that still remained. Well, you continue forward. You're now working on this blue highlighted, and I'll actually erase that because I'm going to be using that, but you're now going to start working on this blue highlighted polynomial. So what I'm going to do is I'm going to try negative 1 again, because who knows? Maybe negative 1 is a 0 of multiplicity 2. So I'm going to go ahead and, because I want to try it again, notice how I do this. I don't rewrite the whole thing. There's no point. Because if I did rewrite the whole thing, let's say that I was like, oh, let me see if negative 1 is a 0 for this polynomial right here. So that'd be a 2. Let's see, a negative 1. I'm just writing down the coefficients, and a 9. Well, notice I could have avoided all that handwriting just by taking my last answer and trying negative 1 on that last answer again. So that's what I'm going to do here. Bring down the 2. 2 times a negative 1 is a negative 2. Add those up. That's a negative 3. Negative 3 times negative 1 is 3. Add those up. That's a negative 15. I can tell you it's not going to work. Negative 15 times a negative 15 is a positive 15, and that is non-zero. So I know that negative 1, this is not a multiplicity, or not a zero of multiplicity 2. So I'm done with the negative 1s. In fact, I'll go ahead and erase that there. Now I'll go to the plus or minus 3s. So let's see, the polynomial I'm still working with is this polynomial right here, even though it doesn't look like a polynomial. Those are the coefficients. And instead of trying negative 1, I will move on to the positive 3. That's the next one in line. Remember, 1 we've already tried. It doesn't work. Negative 1 we tried. It worked once. It doesn't work twice. So now I'm going to go ahead and try the positive 3. Again, you could totally do this by factoring by grouping. It just happens to be with this one. But I'm going to still go ahead and do it this way. Bring down the 2. 2 times 3 is 6. Add them up. 5 times 3 is 15, which gives me, what is that, a negative 3? Negative 3 times 3 is negative 9. Add them up, and lo and behold, we get that wonderful 0. Which means that positive 3 is actually one of our other zeros, which means that this polynomial function, that is, that we were working with, can be further factored into, again, let me just zoom out actually. We found that positive 3 is one of the other zeros, so x minus that positive 3 must be a factor. And we're left with a 2x squared plus 5x minus 3. Now that I'm not going to bother using synthetic division on, because I can actually just factor that using old school factoring techniques. So this is going to be x plus 1 times x minus 3 times, and then this will be a 2x. I'm just doing factoring a guess and check method. Let's see, I need a 3, so let's make this a 3, a positive, and a minus 1. Let's double check that. That'll be negative 3, positive 6, minus 1. Yep, that works out. So that is how that polynomial function factors. And they did ask me actually find all the rational zeros, so I should state them. Remember the zeros, if x minus c is a factor, then c is a 0. So our zeros are x equals negative 1, x equals positive 3. I'm just looking at these guys right here. What turns that into 0 is 1/2. And finally, what turns that into 0 is a negative 3. Those are our zeros. They're all multiplicity 1, and our factorization is just right up here. And that is using a rational roots theorem. Now, notice I didn't have to do really a ton of work. I just listed out some candidates and tried them, and it worked out well. All right, in this next example, I actually cleared it out just because I think that that example that I originally had was sort of broken, just because you end up with something that doesn't have rational roots. So I would like something that actually allows us to practice a little bit more. So this one's a little bit different. It says factor and graph. So let's go ahead and write out the constant term and the leading coefficient. And now that that's done, we're going to go ahead and factor, write out all the factors of those numbers. Now that's quite a few, right? 28 plus or minus 1 goes in that, plus or minus 2, plus or minus 4, plus or minus 7, and let's see, plus or minus 14 goes into that, and plus or minus 28. Shouldn't be missing any in there. I think we're okay. And then as far as the leading coefficient, plus or minus 1, plus or minus 3, and plus or minus 9. That's quite a few options. So I'm going to go ahead and write out just some candidates. I don't want all the candidates. That'll take forever. So instead, I'm going to write out a few here that I want to do. So maybe I'll try the plus or minus 1, maybe the plus or minus 2. Maybe I won't go in the plus or minus 4 yet. Maybe I'll try a plus or minus 1/3. maybe a plus or minus, let's say 2/3. And from there, I will have to make choices as I move forward. But I'm thinking at least right now that's pretty okay. I'm going to start with the positive one. So, and there's my polynomial. So positive 1. Let's see if that is a 0 of this polynomial. And this is a good example to showcase that you're going to spend a little bit of time trying before you have success. That's just how it works here. Let me make sure I have everything. 9, 60, negative 28, negative 1, negative 52, and 28. And I'm not missing any powers on x. 6, 5, 4, 3, 2, and a 1. That's perfect. All right. Bring down the 9, multiply by 1, add them up. 69. 69, and add them up. And 49, add them up. And 57, add them up. This is why starting with the 1's nice, because it's pretty quick to do the 1's here. But you can easily see, hopefully, that this is going to lead nowhere. You get that this is non-zero, so you immediately know the positive 1 is not a 0. So I'm going to go ahead and, I don't know if I want to erase that from my list, because I want to make sure that I remind myself I did it. So I tried the positive 1, that didn't work out. So now I have to do another guess. Let's try the negative 1. And I was going to erase my work, but I won't. I'll just negative 1, 9, 60, negative 20. So I could have paused the video and just written this out very quickly, but it's kind of nice to give you time to think. Negative 1 times 9 is a negative 9. Add those up. Now, probably the biggest mistake that happens here is arithmetic, myself included. So just be very careful when you're doing this. I'm talking while I'm doing my mathematics, which always can be bad. And let's see, that's negative 80. That's positive 80 minus 52. So that's, what is that, 28? And now you can see negative 1 times 28 is negative 28. And we have ourselves a winner. So I know that negative 1 is a factor. So I'm going to write that in green. Rather than rewriting my polynomial, I just have this in green. If you don't use colored pens or anything like that, that's fine. You could just remind yourself by pointing an arrow that negative 1 is not a factor. Negative 1 is a 0. So x plus 1 is a factor. Now I'm going to try negative 1 again. Notice I didn't bother rewriting that polynomial with a factor in front of it. There's no need. So let's go ahead. Bring down the 9 again. Negative 1 times 9. 51 minus 9. What is that? 43? Seems about right. This would be a negative 43. I can kind of tell right now this is starting to grow, and I don't like that. This is negative 114. Multiply it by a negative 1. It's positive 114. Again, I can see that this is going to be pretty bad. So let's see. 80, 94, 93. 193, I think. Let me double check that. 180, 193. Yes. Times a negative. Yeah. You can easily see this is going to lead to a non-zero there. I don't even need to bother. I know it leads to a non-zero. So I know that negative 1 is going to be a 0 only once and no more than that. Okay. So we have one of our zeros. Now I'm going to go ahead and move on. I have now conquered that easy candidate. I'll just cross that out now. We go to plus or minus 2. And you can see again that this is going to be a long-winded process, but we could do it. So again, I'm going to steal this. This is the last set that worked because you have that green 0 at the end of it. And so I'm going to copy those numbers, 9 and a 51 and a negative 71, 79, negative 80, and a positive 28. And we go ahead and start the process all over again, right? So bring down the 9, multiply it by 2, it's 18, that's 60, 69. Multiply that by 2, it's 120, 138. And at first I start kind of getting a little bit gun shy about this because I see that number starting to grow, and in the end, I'll have a 28, then I need to have a negative 28 to cancel it. Luckily, I have 138 minus 71, and so that will be a little bit better because it doesn't seem like it'll terribly grow without bounds. But this will be 67, and twice 67 is going to give me 134. And we're going to add 79 to that, so that will give me 213. And I can tell you right now, this is not going to work out, because if you multiply 213 by 2, it just becomes massive, and subtracting 80 from that is not going to take you down to a negative 28. It actually takes you to a 346. I know this is not going to be 0 right here. Don't worry about that. So I know that positive 2 is not going to work. So now I move on to negative 2. Again, the last working example I had was with the 9, the 51, the negative 71. So I'm just rewriting these. Like I said, arithmetic computations will likely be the Achilles heel. People usually do make arithmetic mistakes. That's just how it is. So be very careful as you go through. You might want to keep a calculator handy because, well, that can be very useful. So let's see. We get a negative 66 here. We're going to lose 71, sorry. And that'll be a negative 137. We're going to multiply that by a negative 2, which is 274. And we are going to, is that right? Yeah, and then we're going to add to that 79, and that will be 353. And we'll multiply that by a negative 2 to get a negative. Now you can easily see this is not going to, right? You add those two up, that's negative 786. You multiply it by 2, it's just not going to be a negative 28, I'll tell you that. So again, negative 2 doesn't work. And great example to showcase how exhaustive this process can be. It's just a really, really hard process to go through. So I'm going to cross out this plus or minus 2. I'm going to go immediately to the plus or minus 1/3 and then the plus or minus 2/3. Yes, I could go to plus or minus 4, plus or minus 7, plus or minus 14, but I'm seeing that as these numbers get larger and larger, all things are swinging wildly at the end with my computations, right? I get these very large numbers of like 193 and 786, whoops, and 346. So as those numbers get large, it looks as though it's not very good. So I'm going to go back to smaller numbers. The 1/3 and the 2/3 might be good choices. So I'll swing over to the 1/3 here. And remember, the last known good line we had was this guy right here. So I'll go ahead and copy that. And we're going to do positive 1/3. Copying. There we go. Bring down the 9. Now, fractional zeros are a bit intimidating because you're dealing with fractions, right? But luckily, 9 times 1/3 is 3. Add 51 to 3, and you get 54. Divide that by, or multiply that by 1/3, if you will. Let's see, 3 goes into 60 20 times, but you're 6 shy, so it goes in 18 times. And 18 minus 7. So this is where I kind of quickly run through with a calculator. 18 minus 71 is a negative 53. And here's where I get very concerned. Because if you divide that by 3, it is a fraction. So this would be a negative 53/3. And now it gets ugly. So I might pause here because it doesn't go in cleanly. So I'm going to pause for a minute, and I'm going to go over and try a negative 1/3. Doesn't mean that I'm throwing that out. It's just that it started getting ugly, and I don't want to do fractional arithmetic all day long. So I'm going to go ahead and move on and see if there's a different 0. If not, I'll come back to that. But I really start with this idea that maybe I can, I can stick with simplicity, right? Let's see, this is negative 16. Let's see, negative 71, lose another 16 is a negative 87. 1/3 of 87 actually is, what is that, 29? And this is definitely not meant to be a lesson in arithmetic. It's just what you have to kind of go through with this. You add those up, it becomes 108. 108 is divisible by 3, actually. Let's see, a negative 36. Negative 36, lose another 80. You get 116, which is not divisible by 3. If the digits don't add up to a number that's divisible by 3, it's not divisible by 3. So this is going to be a positive 116 over 3, which is non-zero. I can kind of throw that out. And it starts looking like it's just a super long process, right? We only found 1 0 so far, which is super not satisfying. Let's try the 2/3 and negative 2/3. And because I happen to know where the zeros are for this, I'm going to go ahead and actually, it's fine. We can just try the 2/3 because I think 2/3 ends up being a 0. So let's try it out. 9, 51, negative 71, 79, negative 80, and a positive 28. Bringing down the 9, divide it by 3 and multiply it by 2. So that'd be 3 times 2 is 6. Add them up, that's 57. Divide that by 3, which is 19. And then multiply by 2 is, did I say 19? Yeah, I did. Multiply by 2, that's 38. And add those up, it's a negative 33. Negative 33 divided by 3 and multiplied by 2. So that'd be 11 times 2 is 22. So a negative 22. Add those two up. What is that? 51? 57. 57. Divide 57 by 3 is 19 times 2 is 38. And lose 80 from that. 50, 42. Yeah, negative 42. And let's see, 42 divided by 3, 13, 14 times 2 is 28, negative 28. Aha! So I do find that positive 2/3 is yet another 0. And sorry about that last little inking there. Zoom in. Positive 2/3 is 0. And remember, when you find out that something is a 0, try it again. So I'm going to try 2/3 yet again. Once I find one, I latch onto it. So let's try a positive 2/3 again. By the way, you should pay attention to the degree of your polynomial. Right now, this would be a polynomial of degree 0, 1, 2, 3, 4. So I'd like to get it down to 4 terms or less. So I can use either factoring by grouping or factor a trinomial. Checking to see if 2/3 is yet a 0 again. 9 divided by 3 is 3, times 2 is 6. Add those two together, that's 63. Divide that by 3 is 21. Times 2 is 42. Lose 33, that's going to be 9. Double check my math on that. Yep. Divide that by 3 is 3. Times 2 is 6. Add 57 to that, that's 63. Divide that by, oh, look at that. It's like a little repeating pattern. That's going to be 42. And that will actually add to 0. So again, 2/3 is a 0 yet again. Point a little arrow at that. I'll point to, yeah, I already did that. So now we have 1, 2, 3 zeros already. Well, I don't want to say already because that's a lot of work. And now we're down to something, if you look at our result there, that will be a polynomial with 4 terms. And the terms are 9, 63, 9, 63. I easily know that will factor. So that's a factoring by grouping. So I know that our polynomial, which I'm not going to rewrite the whole silly polynomial, I'll just rewrite it like this, has the factors x minus a negative 1, so x plus 1, and an x minus 2/3 twice, so multiplicity 2. And then we have 9, let's see, this will be the 0th or the constant. This will be x to the first. That will be x to the second. So this will be x to the third. So 9x cubed plus 63x squared plus 9x plus 63. And you can see that from both of those terms, they're both divisible by 3. I'm sorry, both those groups is what I meant to say. This group and the other group have 3 in common. And the first group you can also factor an x squared out of. So that's what I'm going to do here. So this will equal, we have an x plus 1 times an x minus 2/3 squared. Again, I'm going to factor out of that first group a 3x squared. If I do that, is that right? No, because they're both divisible by 9. 9 goes into 9, and 9 goes into 63 7 times. So that's perfect. 9x squared. And I'm left with x plus 7. And this one, a factor out of 9, I'm left with an x plus 7 there as well. Factoring by grouping is beautiful because these two terms have an x plus 7 in common and a 9, technically. Might as well factor those out too. So let's go ahead and do that. This will be x plus 1 times the quantity x minus 2/3 and quantity squared times. So I'm going to factor out of the first term here a 9x plus 7. Also, that gets factored out of the second term. And what I'm left with is the single little x squared right there and a 1. And you can see my full factorization is as follows. 9 times x plus 1 times x minus 2/3 quantity squared times x plus 7 times x squared plus 1. Lots of work. Now remember, we were actually asked to graph this. And so we get to use some of our ideas that we've gone through in the past here. I'm going to draw out the x-axis. I know the overall degree of this polynomial, since they handed it to me initially this way. It's a 6th degree polynomial with a positive lead coefficient. So I know the end behavior of this polynomial is going to be up, up, like a parabola. So I'm going to write end behavior here. End behavior. It looks like that at the endpoints. And now I'm going to worry about the zeros. Well, we know that -1 is a 0. Let's list out our zeros and their multiplicities. So -1 is a 0 of multiplicity 1. 2/3 is a 0 of multiplicity 2. And by the way, I'm assuming that you've watched the prerequisite videos, because obviously I'm assuming that, right? -7 is a 0 of multiplicity 1. And then x squared plus 1, there's no way that can turn into 0, so there's no 0 provided by that factor. So these are the only zeros you have. Now that allows me a little bit of knowledge about the scale here. So if this point right here was -1, I might call this -7, and positive 2/3, let's just say, is right about here. I know that it's going to start high. I know it's going to end high because that's the end behavior. Now let's go ahead and focus on the fact that at -7, and I apologize that negative didn't look right. At -7, it's going to look like a line locally. So it's going to start tall and look like a line as it crosses through. And if I zoom in on that, it totally does look like a line locally. So it's crossed through x equals -7. Like a magnet, it's going to be drawn back to x equals -1, where it's going to cross through again like x to the first, like a line. So you notice how I do that? I just kind of make that happen. And again, it'll like a little magnet, it's going to be drawn back down to the next x-intercept, which is at 2/3, and that has multiplicity 2, which means it's going to look like an x squared, right? It's going to look like a parabola as it approaches that. So it's going to look something like that. There you go. And I often have to tell students that I will miss my up arrows. If you do that, you just erase and fix it. And the y-axis is likely somewhere around here. Actually, I probably drew it a little too far to the left, but that's not that big of a deal. And that's a semi-accurate graph of p of x. We just had to factor the original polynomial. And it took a lot, right? So the rational roots theorem is really a great theorem, but you can end up spending a lot of time trying until you find those zeros. So just a proper heads up on that. All right, so let's go ahead and take a look at the next example here, because you really want to be able to create your own examples. That's actually the skill set of a really good student, is somebody who can actually create their own examples as they go through, and so they can challenge themselves essentially. So how do you do that? Well, start by picking some zeros. Pick as many as you want. You don't have to be too crazy, but pick some zeros in their multiplicities. So for an example, actually how I built that last example is I picked zeros like, let's say 3/2 and 1, and let's say 2, and maybe 7, and let's throw another one there like a -4 or something like that. Okay, and then I worked out their multiplicities. I just said, well, how do I want their multiplicities to look? So here I just said I want the multiplicity of this to be, let's say 2. Say you want the multiplicity of that to be 3. Maybe a 1 on that, and a 1 on that, and maybe a 4 on that. Now this is going to be a massively large polynomial. However, something you need to know, if those are the zeros, then x minus those are going to be the factors. There is one exception here. So let me just showcase this. If I were to build this, let me ignore the 3/2 for a moment. I know that x minus 1, let me zoom in here. X minus 1 will be a factor of multiplicity 3. I know that x minus 2 will be a factor. I know that x minus 7 will be a factor. And x minus a -4 will be a factor, and that'll have multiplicity 4. Now, I didn't write the 3/2 there because I don't want to write it this way, x minus 3/2. If you did that and you went to the next step, which is to go to Wolfram Alpha to multiply this out for you so you can then try to factor it, it would give you a bunch of fractions. And that is not nice. We don't want fractional coefficients. We want all of our coefficients of our polynomial to be integers. So the way you can get around this here is imagine that, okay, we were told x equals 3/2 is a 0. Imagine multiplying both sides by 2. You don't have to imagine, I actually just did it. And then you subtract 3 from both sides, and that is actually a better way to write that factor. And remember, we said it was going to be of multiplicity 2. So that's how I would write that factor, not as an x minus 3/2, but instead a 2x minus 3. It gives you the same 0, which is 3/2. It's just much better because you now have integer coefficients. And remember that the rational roots theorem works with if you have integer coefficients. It didn't say anything about non-integer coefficients. So you need to force integer coefficients. Okay, so now what do? Well, you go to Wolfram Alpha and have it expand that polynomial for you, and then you try factoring that using the rational roots theorem. Of course, you already know the factors, but it's a good way to practice. So let me just showcase how I would do that. I'm going to grab this polynomial right here, and I'm going to let Wolfram Alpha multiply it out for me. And you can see all I did, I'm at wolframalpha.com, and I just typed in the polynomial that I want it to multiply out, just so that normally you would never do this. But if you're making your own examples, it's perfectly allowable. I just hit enter, and what's going to happen is it's going to take a few moments to actually multiply that out because there's a lot of computations in the background. And it took maybe about 20 to 30 seconds, but it finally got down to it, and you can see here it is. Now, I got to tell you, the first part of my advice on getting or grabbing roots is don't go crazy. And what I did there with just grabbing a bunch of them, putting a lot of power on it, is I went crazy. And so I have 32,256 as my constant. I don't really want to go through that. So I would probably clamp down those numbers on this quite a bit. And there are two ways to go about that. You can either reduce powers. So like the problem is the fourth power of this 4 is going to be a very large number. I think it's 512. And so if that's the case, 2d8, no, it's 128, 256. So anyway, it doesn't really matter. But the reality is that will give us a large constant. Then you're going to multiply that by 7, and then you're going to multiply that by 2, and then, well, 1, who cares? And then 9. So you might want to take some time to reduce these numbers and their powers a little bit, but you get the idea. You can make your own example. Just choose your roots. And like I say over in the method, don't go crazy with picking zeros. And then if you do that, you have Wolfram Alpha multiplied out for you. And then you could go ahead and just use the rational roots theorem. And then I say, if there is time, we can do this. Otherwise, just try it on your own. Just try it on your own. Again, do not pick large powers on large numbers. It's okay to pick a large number like 7, but it's not okay to make that like a 7 and have a multiplicity of 10 on it, because it'll just be ridiculous. It's safer, I think, when you're creating your own examples, to keep the numbers somewhat small, right? The 1, the 2, the 3 halves even. But for the 1, you could do a high power on that, because 1 cubed is still 1, so that doesn't really adjust anything. And even a 2, you could put a square on it if you wanted to. But as the numbers get large, that constant will get massive. So that's how you can make your own examples. I highly recommend it. It's a great practice. And so finally, I just want to mention, this is kind of tying things all together, that polynomials end up being incredibly valuable in mathematics and engineering. It turns out that many of our functions, whether they be logarithms or exponentials or trigonometric functions, it turns out that many of them can be represented by infinitely long polynomials. Now, I am kind of letting something out of the bag here when I say this, but something like e to the x, that is actually an infinitely long polynomial. It's 1 plus x squared over 2 plus x cubed over 6 plus dot, and it goes on forever. It goes on forever and ever and ever. But being able to factor polynomials ends up being very powerful. Also, being able to quickly evaluate them, divide them, or find their zeros is of utmost importance. So in this, the last few lectures, we've talked about the synthetic division and the rational roots theorem and the remainder and factor theorems. All these can be very powerful if you remember them. If you forget them, you end up wasting time on other older methods, or you'll just be stuck. So this chapter is dedicated to an in-depth exploration of polynomials. And it's totally understandable if all the new techniques might make you feel a bit overwhelmed. So I want to just spend a moment here summarizing. Now, when given a polynomial, there are many things you can do with that polynomial that can seem different from one another, but they're actually the same. So for example, evaluating. If I hand you a polynomial and I say, I want you to evaluate this polynomial. So if your ultimate goal is only to evaluate a polynomial, let's say at C, well, then you can just either, 1, plug in the number C to the polynomial, which is fine, but it ends up being a little bit of a tough method if you have a large polynomial. The other option is to use synthetic division, right? Because we know that if you use synthetic division with C, the remainder, whatever that number is for the remainder, is going to be P of C. And often I think that using synthetic division and using that remainder is faster, honestly. So for practice, you should just try using synthetic division to evaluate polynomials for a while instead of direct evaluation, because you just might be surprised at how much faster synthetic division is compared to direct evaluation. Each time you evaluate a polynomial, you actually find several pieces of information. So if for example, P of C is equal to some number R, then once you've evaluated that polynomial, you find out that R is the remainder. That is the remainder when P is divided by X minus C. So essentially, when you evaluate a function, let's say you evaluate a polynomial and you get the answer 5, that means that that polynomial divided by X minus that 5 is equal to some other polynomial that you didn't find yet, plus that remainder of 5 over X minus X minus C. So if you evaluate a polynomial at, let's just say 1, and you get out an answer of 5, that's what I should have said, then that's basically saying if you divided that polynomial by X minus 1, it would end up being some, who knows, polynomial plus the 5 divided by X minus the 1. So you find that remainder divided by the divisor. So that's one thing you get whenever you use evaluation. So that's kind of critical. Another thing to recall is that if the polynomial evaluated at some value C is equal to 0, well, then you know that there's no remainder when you're dividing by X minus C. So no remainder for P of X divided by X minus C. So that's kind of nice. Additionally, if you're going to graph the polynomial, we know that it will strike the x-axis at C. That is, it also implies C comma 0 is an x-intercept. So evaluations give you a lot of information. Again, to do an evaluation, you just plug in C, or you use synthetic division. The outputs of an evaluation tell you a remainder when dividing by X minus C. And if the output of your evaluation is 0, that means there's no remainder when you're dividing by X minus C, which also means that C comma 0 is an x-intercept. Anyway, basically the punchline is that using synthetic division to evaluate polynomials can lead to very handy information. Let's spend a brief moment just tying things together for factoring. We know that factoring, evaluating, and division are intimately tied together. If your goal is to factor a polynomial that generally would be impossible to factor by any other means, well, make sure it has integer coefficients and then use the rational roots theorem to find the other rational zeros of the polynomial, or basically to find all the rational zeros of the polynomial. In this process of finding those rational zeros, you're not only finding zeros, but each zero leads to a linear factor of the polynomial. And we've seen that in previous examples. So if you found that x equals 1 is a 0 and x equals 2 is a 0, and let's say that's of multiplicity 2, then you know you have factors x minus 1 and x minus 2 for your polynomial squared. So factoring and finding zeros is intimately tied when it comes to polynomials. And finally, when you talk about graphing. So graphing is, well, kind of the end-all be-all in mathematics. So if given the graph of a polynomial, you can ballpark these zeros, which are the x-intercepts, and their multiplicities by just taking a look at the graph and building a functional representation of the graph. So again, somebody handed me this, and let's pretend it did something like that, and it crossed at -8, -5. I'm kind of going quickly. -3, and let's say this is +3. I can use the shape, the overall shape. The fact that it goes low, ends high tells me it's odd multiplicity is what, or odd degree is what the polynomial is. I can easily see that it goes through it has a 0 at x equals -8. So x plus 8 is a factor. It looks like a line at x equals -8. So the multiplicity of that factor is going to be a 1. It goes through x equals -5. So -5 is a 0. So x plus 5 is a factor. Again, it looks like a line as it goes through that. So I'll just put a power of 1 on that. It goes through x equals -3, as sloppy as I made that. And it looks like a line. So x plus 3 is a factor. Again, degree 1, because of the fact that it looks like a line when it goes through. And finally, it goes through x equals 3. And this time you might say, oh, it looks like a parabola. I would argue that it doesn't look like a parabola as much as it looks like a really high degreed, even powered function. So I would say the multiplicity of 3 is not just even, but it might be a 4 or a 6, because if it were a parabola, it would look like that. Go through nice and smooth, kind of a U shape or something like that. But because it gets really flat, I know that the even power is going to be higher, maybe a 4, a 6, an 8, or something like that. So I'm going to go ahead and say that 3 is a 0. So x minus 3 is a factor. And it's of multiplicity, maybe 6, let's just say. Now, if you count up the powers, 6 plus 1 plus 1 plus 1 is 9. That's an odd multiplicity, or an odd degree. And notice we said the degree of this polynomial should be odd. So I'm going to say that that's my polynomial. It works out. So again, everything kind of ties back to zeros, factors, and multiplicities. And that might not be the best tie together, but honestly, I've been recording for days upon days, and so I'm just tired. So, all right, I hope that helps out a little bit, and I'll see you in the next lecture.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.